A few parting thoughts on this example from the previous video. For the total area from -2 to 3, it's important to note that we cannot just do this. Because what that's doing, if we refer to the calculator, is it would be finding the 7.88 plus -2.67, adding them together, then taking the absolute value. You have to remember the order of operations. So when we're finding the total area from -2 to 3, you do have to split it as such, integral from -2 to 1, and then integral from 1 to 3, the absolute value of that. Or, as we saw previous to this example, we could find the integral from -2 to 3 of the absolute value of the function. And that's going to take this portion here and reflect it up above the x-axis, which is something we saw when we were doing function transformations. So let's do that. I have my function ready to go. I'm going to put absolute value around it. I press enter. Now you see this region here was reflected above the x-axis. If I go into Analyze Graph and take the integral from -2 to 3, there's my total area of 10.5, which is the sum of these two smaller areas. Remember, the 2.67 is the absolute value of what was there. So 2 more examples today. Find the area of the region bounded by the graph y equals 1 over x squared and the lines y equals 1 and y equals 4. Okay, so if we graph that, there's y equals 1 over x squared, roughly. Not a great sketch, but it is what it is. And if you remember back with the fundamental theorem of calculus, with all these theorems that we've been seeing, it says that f has to be continuous from a to b. So going from here to here or something like that, f isn't continuous between those values, so we can't take the antiderivative. We can't use the fundamental theorem of calculus. Oh no, what do? Well, we're integrating from 1, y equals 1, to y equals 4. And we want this area. Well, there's nothing that says that we have to integrate with respect to x, and we're not gonna. Our limits of integration are 1 to 4, and we're going to be integrating with respect to y. We're going to be able to find the area bounded by the curve, the lines y equals 1 and y equals 4, and the y-axis. So we're going to start by finding that area, and then multiply by 2. Okay, but how do we do that? The function says y equals 1 over x squared. I can't integrate that with respect to y. Well, sidebar, we actually could, but it wouldn't do us any good. Hey, that rhymes, kind of fun. What we're going to do is we're going to rearrange this formula. We're going to solve it for x. So x squared y equals 1, x squared equals 1 over y, x equals the square root of 1 over y, which is y to the -1/2. Now I'm in a position where I can find this definite integral, multiply it by 2, and have my area. The thing to note before we get going with this is the boundary values were y. So we need to rewrite the function in terms of y. So let's do it. Actually, you know what? Pause the video, see if you can do it. So 2 times, we increase by 1, multiply by, or divide by that new power, evaluate at 1 and 4, so we have 2 times square root of 4 minus 2 times square root of 1. So the total area is 4 square units, and that would be all of this, both sides, because we multiplied by 2. Next example, find the area bounded by y equals x cubed plus 1, the y-axis, and y equals 1 and y equals 9, those two horizontal lines. So let's start by sketching the graph. And you should be able to sketch an x cubed curve that's translated up 1 units. You definitely don't need your calculator for this. But we're going to look like that. That's y equals x cubed plus 1. This has a y-intercept of 1, and we're dealing with horizontal lines of y equals 1 and y equals 9. So the area we're looking for would be this one. Again, we're going to be integrating from 1 to 9 dy, not dx, because our limits of integration are y values, not x values. We want the area bounded by the curve, the boundary lines, and the y-axis, not the x-axis. So we have to rearrange that guy. Y minus 1 equals x cubed. X is the cube root of y minus 1, or y minus 1 to the 1/3. Since the thing we're integrating inside the base of the power is more than just y, I'm going to do a little substitution. U equals y minus 1, du is 1 dy. So the u substitution doesn't really help us here. There's no inverse chain rule that we need to apply because the coefficient of y is simply 1. This becomes y minus 1 raised to the 4/3 times 3/4, evaluated at 9 and 1. So this would be 3/4. I'm going to factor the 3/4 out this time. 8 to the 4/3 minus 0 to the 4/3. Well, 8 to the 4/3, that would be 2 to the 4th, which is 16. My area is 12. Another way that we could have done this would have been to find that area, and that area x is 2, integrating from 0 to 2 of this function, and then subtracting this red area from the area of that big box. I'm not going to go through it. I would challenge you to find that red area that I shaded in, and find the area of the blue shaded box and subtract the two, and see if you get 12. If you don't, see if you can seek out some help with this problem. And we're going to go one step further today. We're going to find the area between two curves. So if f and g are continuous on the interval a to b, and f of x is always greater than or equal to g of x for all x on that interval, then the area enclosed by those two functions is simply the area of the top minus the area of the bottom, and that should make sense. This blue part would be the area under the f of x curve. Subtract off this part I'm shading yellow, which is the area under the g of x curve, and that gets us the pretty pick in between. And using our properties of definite integrals, we could just find f of x minus g of x and then integrate from a to b. Now, one thing to think about, if there's multiple regions, such as what I've shown here, what you have to bear in mind is that at point C here, at x equals c, the functions switch roles. And now g of x is the top function, f of x is the bottom function. So to find the integral from a to b here, what we would actually need to do is find the integral from a to c and then add to that the integral from c to b, g of x minus f of x, because the top and bottom functions have switched roles. And let's look at an example. Find the area of the region in the first quadrant that is enclosed by y equals square root x, the x-axis, and the line y equals x minus 2. Guess where we start? Draw a picture. So there's y equals square root x minus 2 would be going something like that. It intersects the x-axis right there at 2, 0. And the big question is, where does it intersect the curve square root x? Well, to solve that, we set the two equal to each other. We're going to need to do a little algebra here. Square root x equals x minus 2, so x equals, I'm squaring both sides, minus 4x plus 4. X squared is, I'd have x squared minus 5x plus 4 equals 0, and that's factorable, x minus 4 there's our factored form. We get x equals 4, x equals 1, and you're thinking, wait a minute, I know I was thinking it, but x equals 1 is not a point of intersection, and what happens when we substitute that back here is we find that it is extraneous, that does not work. So this point is 4, 2 is where they're intersecting. The area that we're looking for is all this. And in order to find it, we actually have to split it into two parts, because this part that I'm coloring in blue is bounded by the curve and the x-axis. The part that isn't colored blue is bounded by the curve and the line. So to find this total area, we're going to integrate x to the 1/2 from 0 to 2, and then add to that the integral from 2 to 4, square root x minus 2 dx. So pause the video and evaluate these two definite integrals and see where you get. So here are our antiderivatives. Now we're going to substitute the limits of integration in. We get 4 root 2 over 3 minus 0 plus 16/3 minus 4 root 2 over 3 plus 2. And this is equal to 10/3. So there is our area between these two curves. I hope you're coming to the conclusion that to successfully find these areas, a sketch with points of intersection and such is really, really pivotal to doing well. And that is where I shall leave you. Enjoy all the practice you're about to do.